Okay, what we're going to do is our first integration by substitution. Let's explain why we want to do this one by substitution. The integral we're looking at is the double integral where the integrand is just 5, that's fine, where the region is this parallelogram. The reason we would want to do a substitution is because if we do this with respect to dx first, we'll have 3 different integrals. If we do this with respect to y, we get 3 different integrals. And even if we use polar, there's 2, so we're not going to do that. So what's going to happen in Calc 3 is that we're going to be handed a substitution. We won't have to come up with a substitution. We're probably going to have to use it. And the idea is to use that substitution to get an integral in terms of u's and v's. And then we're going to see where an extra term actually comes up. Now when we make the substitution, this region is going to turn into something with u's and v's. So what I actually need to do is look at my substitution here and realize that this is the substitution that I can plug in u's and v's and get x's and y's. I want to undo this so I can plug in x's and y's and get u's and v's because I want to plug in those points. So what I'm going to do real quickly is just to rewrite this as a matrix equation. I'm going to leave a big gap right here. This is going to be 4 and 3 and 2 and 5. And what I'm going to want to do is multiply both sides by the inverse of that matrix. You can row reduce if you want. I'm doing this way instead. I know that I switch those two. I change the signs of those two. And then we have to divide by the determinant, which is 14. And I have to do that on both sides. So I get 5 minus 2, and that should be minus 3, I believe. Minus 3, 4, 14 like this. And I'm just going to multiply everything out. This matrix and this matrix are inverses, which means when I multiply them together, I get the identity matrix. The identity matrix times any vector is just the vector. Or I'm very happy about that. And what I'm going to get is this thing over here. And I'm just going to write out the equations on the bottom, then I'll slide them up and we'll use them. So what I'm going to get is that u is going to be 1/14 times 5x minus 2y. And then I'm going to get v is equal to 1/14 times minus 3x plus 4y. And this is going to be the substitution I'm going to make so I can plug in those points and find out what happens to those points when I turn them into u's and v's. So I'm just going to slide this up. And we're going to have a table. So I'm going to have x's and y's. We already know those. I want to find out what u's and v's I get, so this is supposed to be 1/14. And I want, this is 5x minus 2y. V is going to be 1/14 times minus 3x plus 4y. Now that we have that, I can start plugging in the points. I know that when I plug in 0, 0, I'm just going to get 0, 0. So that one is just absolutely trivial. When I plug in the point 4, 3, plug in the point 4, 3, I'm going to get 20 minus 6, that's 14. 14 divided by 14 is 1. You can see where we're making that substitution. When I plug in 4, 3 over here, I get minus 12 plus 12. That's going to be 0. So this thing turns the point 4, 3 into the point 1, 0. We also have 2, 5. When I put a 2 right here and a 5 right here, I get 0. When I put a 2 right here and a 5 right here, that's minus 6 plus 20, that's 14. 14 divided by 14 is 1. I get that. And when I plug in 6, 8, this is a linear transformation. I should just get this point plus this point, but we'll see. I'm going to get 30 minus 16, that's 14. 14 divided by 14 is 1. I get minus 18 plus 32, that's 14. 14 divided by 14 is 1. And you can see that this transformation turned the 4 points 0, 0, 4, 3, 6, 8, 2, 5 into the points in the UV plane 0, 0, 1, 0, 0, 1, 1, 0, 1, 1. That's a wonderful thing to have. I don't think I need this anymore because I want to draw the new region. Draw the new region. This is going to have u's and v's in it instead of x's and y's. Much, much nicer region. If I just start writing the new integral. We're going to see, for example, 5 is just 5. I'm not going to have a problem with that. I am going to put du dv over here. I'll worry about what happens with that. I just get 0 to 1 and 0 to 1. Right? Now, if this is our correct answer, we could evaluate this really easily and get 5. And 5 feels like it could be an answer. The problem is that if you look at my original integral, what I actually have here is a giant French fry, where the bottom of the French fry is this parallelogram, and the roof of the French fry is 5, right? The actual answer should just be 5 times the area of the parallelogram. Well, the 5 is just a 5. The area of this parallelogram is actually the determinant of this matrix. Remember, that's how the determinant is defined, and we know how to take the determinant of a 2 by 2. We're just going to get that 14 that kept showing up all over the place. Now, that 14 is going to be really, really important here, because when we made a substitution, we just saw what happened to the region. It turned the region into something nice. The integrand was just the integrand. But if we don't add something or put something in right here, we're going to get an answer that needs to be a whole lot bigger. How much bigger does it need to be? It needs to be the determinant of, I'm going to call it A for the moment, and we'll talk about how we get A. Now, here is our original substitution. Now, in general, our substitutions won't be linear, so we can't just say take the determinant of the thing. However, if you notice, the determinant we actually got here you can get by taking partial derivatives. For example, the 4 that I want is going to be the partial derivative of x with respect to u. The 2 that I want is going to be the partial derivative of x with respect to v. The 3 that I want is going to be the partial derivative of y with respect to u. The 5 that I want is going to be the partial derivative of y with respect to v. And this is the determinant that needs to go right in here when I substitute. Because what we did is we took one giant big French fry and turned it into a French fry with the same exact height but a much smaller area in the base. So in order to actually make sure that the volume didn't change, I have to make sure that I adjust the area of the base exactly by how much the area got multiplied by. We'll give this a name and some notation in the next video, but meanwhile, that with the 14 restored, we get the answer we wanted, right? And by the way, this integral is a whole lot easier than this one, even if I have to worry about adding an extra determinant into the integrand.